As we start doing the unit on finding the limit of a function by approximation, we'll start by defining what a limit is. And this is the definition that was in the section on finding the limit graphically. Anyway, remember a limit is, this reads as, the limit as x approaches a of f of x equals L, and the idea is as x gets nearer to a or closer and closer to a, what is the value of the function? That is defined as L. And we further divided this up into what we called the left and right hand limits. The limit approaching from the right, or the right hand limit, as you can see, is the limit as x approaches a of, with the little plus of f of x. And again, that's the right-hand limit. And then the left-hand limit is the limit as x approaches a with the little minus from the left, or the left-hand limit. And I can zoom in, you can see the little plus and minus above the a. So, approximate the following limit by choosing values that are close to value in 1. So we're going to do an example where we actually find the limit by approximation. So again, approximate the limit by choosing values that are close in value to 1. So what I'm going to do in this next slide, what we're going to do is pick values that are slightly bigger than 1 or slightly less than 1. So for example, we could use 0.1, 0.01, and 0.001. And these would be values on the right, finding the limit as we approach from the right. Then to find values approaching from the left, we could go 0.9, 0.99, and 0.999. These would be values that are slightly to the left of 1. Now, if you take your calculator, and recall our function is x squared plus 1, if we plug in 1.1 squared plus 1, that'll be 1.21 plus 1, which is 2.21. And realistically, at this point, simple computation like this, I'm not worried about it. What I want you to do is just punch this in your calculator real quick and see if you're getting these results, because we're trying to see what the function's doing. This is kind of an approximation technique, or just experimental. So if we plug in, 1.01 and 1.001, we'll get 1.02 and 1.002. So it appears that, looks like, coming from the right, the limit's approaching 2. Now let's approach from the left. So why don't go ahead and, using the same function again, plug in 0.9, 0.99, 0.999. Again, 0.9 squared is about 0.81 plus 1 is 1.81. The computation, again, is fairly basic. So if you just want to run these numbers on your calculator, I would suggest doing that, and you will get 1.81, 1.98, and 1.998. And again, this appears to be approaching 2 from the left. So your left-hand limit is 2. And you have agreement. So our overall limit, as you can see, will be 2. Now that won't always happen. You may put numbers in on both sides and you have disagreement. And if that's the case, then your limit doesn't exist. With a rare exception where they might be both approaching like positive infinity or negative infinity. Okay, I wanted to do one more example of a limit by approximation. I'm going to evaluate the limit as x approaches 0 of sine of x divided by x. Now recall, if you're, think about, I know ultimately we are on a Cartesian plane, but if you were just to think about x for a second, just worry about x values, what would happen is you would probably want to pick something like 0.1, that's pretty close to 0, then maybe 0.01, and then same thing on the other side, maybe 0.9, and then maybe 0.99. But the idea is you're picking values very close to 0 on both sides. So, again, we'll do 0.1, 0.01, 0.001, 0.9, 0.99, 0.999. So if we do sine of x divided by x, which will be sine of 0.1 divided by 0.1, I'm going to write that down. I'll punch that in the calculator right here. Just give me 1 second. I need to be in radians. Yeah, make sure your calculator's in radians. Yeah, it's 0.998. And again, make sure if you, I don't know if I got muffled when I was over there by the calculator, but make sure you're in radian mode. It's not degree. It won't work with degree mode. Okay. And the reason why that is your bottom is just x by itself. Radians are set up to be plugged in directly as a variable. Degrees, you can't do that. So like if you have like sine of x, you can actually put in degrees. But the value of x itself, if it's algebraic, you cannot use degrees. You have to use radians. Anyway, let me finish this side out. And what you will get will be really very close to 1. So I'll just record that. But you can, I've already done these beforehand. But those two come out to 1. Now let's do sine of 0.9. Divided by 0.9, and that will give me 0.998 again, and the last two result in 1 again. So let me record those. Those both come out to 1. So it looks like I'm running out of space here, as you can see. So I think it's fair to say that coming from the left, the limit's 1. Coming from the right, it's 1. So we do get agreement. So your limit is 1. If you're wondering what the curve looks like, what happens kind of connecting it to graphical limits, you're like saying, what's going on? It's undefined. But yet I have a limit. Well, you have a hole again. And what happens is you zoom in on both sides of what will be 0, 1. You will see the curve gradually comes up and approaches 1. And this, of course, is this, the graph of the function sine of x over x. But you do end up getting a hole in this situation. But you do get a limit, as you learn with the limits graphically. Okay, so we have those two examples. There's more examples in the SOTAN calculus book. So, feel free to work those. Work your WebAssign problems. And email me if you have any questions. The next unit will be on doing limits analytically.